Center, respected council members, corporate members of the Institution of Engineers India, engineers, engineering students, and participants in this webinar. If we look into the reasons for discussion on modern applications, modern approaches in the field of wastewater treatment, we will find that wastewater treatment is crucial in order to protect our environment and health of both humans and animals. When wastewater is not treated properly, it will contaminate water sources, damage natural habitats, and causes serious illness. Chemical precipitation, nanofiltration, algae treatment mechanism, reverse osmosis, ion exchange, ultrafiltration, and bioabsorption methods are among the most recent wastewater treatment methods that have been in use recently. Thus, it is the order of the hour to assess the modern approaches in the field of wastewater treatment. Before the end of my welcome address, I, on behalf of the Institution of Engineers India Tripura State Center, sincerely acknowledge the time and efforts made by Chemical Engineering Division of the Institution of Engineers India Tripura State Center, technical and office staff of the Institution of Engineers India Headquarters, especially Dr. King Shuk Sen, Assistant Director Technical, and Shujit Chakraborty, Deputy Director Technical of the Institution of Engineers India, Chemical Engineering Division Board of the Institution of Engineers India, and supporting staff of our center for organizing this webinar. With these few words, I welcome you all once again and wish a grand success of this program. Thank you.
Thank you, Dr. Bhattacharya, for your very elaborated welcome address. Now, ladies and gentlemen, for our today's first expert deliberation, we have with us Dr. V.C. Padmanabhan of NIT Agartala. Dr. Padmanabhan is working as an assistant professor in the Department of Bioengineering of NIT Agartala. He has earned his BTech and MTech degree from Kamraj College of Engineering and Technology, followed by PhD degree from Anna University. Dr. Padmanabhan, with specialization in biochemical and environmental engineering, has over 11 years of teaching and research experience in the diverse field, with main focus on process development and design of experiments using various mathematical methods. He is a recipient of the Young Engineers Award 2021-22 from the Environmental Engineering section of the Institution of Engineers, Kolkata. He is actively involved in various research projects funded by various agencies and has published more than 45 research articles in reputed national and international journals with cumulative impact factor of more than 190. He has also published numerous book chapters. He is a member of the American Chemical Society, International Water Association, Indian Institute of Engineers, and the International Association of Engineers. His research collaborators are from various institutes of repute, both from India as well as abroad, such as University of Paris, Cranfield University, IIT Guwahati, to name a few. So now I would like to request Dr. Padmanabhan to kindly share his particular slide and start with his expert deliberation. It's all about to you,
Yeah.
Padmanabhan. Thank you.
Yeah, thank you. Just a minute, sir. Yeah, whether my slides are visible, sir? Clear?
Yes, you can go for full screen mode, sir, and you can start with the deliberation.
That's clear?
Absolutely correct, sir. Please go ahead.
Oh, yeah. So, good evening to everyone, and thanks to Chemical Engineering Division Board, IEI Tripura State Center for giving me this opportunity. Without taking much of your time, I wish to take you all towards the journey of water. So in this session, I'll be giving some information towards the theme of the webinar, that is modern approaches in the field of wastewater treatment, and followed by some research case studies relevant to my lecture, that is removal of dye-based recalcitrant from aqueous matrices using radical-driven advanced oxidation processes. So yeah. So before getting into the lecture, let us see the water quality status in India, especially in various rivers and cities. In a very recent study from Yale University, they ranked countries based on the quality of the water supply. Most of the European countries provide safe water to drink with about 93%. Just a minute. Yeah. Above 90, you can able to see close to 90, above 93%. Most of the European countries provide safe water to their citizens, whereas India belongs to the scale of only 18%. And in another study by Central Water Commission, India reports that out of 222 sites, almost 67 sites belong to the polluted sites in the river belts. And out of 445 rivers and 275 rivers are polluted heavily, and the piteous part is 62,000 million liters per day of sewage is dumped into the rivers without any proper treatment. So while urban cities take pride in contributing towards the nation's economy, it also plays a very critical role in polluting the water in most of the water reservoirs. So that is one of the important thing we need to concentrate with respect to the urban cities. We need to take care about the different kinds of water we are handling with. And next one is about the pollutants, the three major categories. So through the recent advancements in environmental engineering and water management, an interesting grouping of water contaminants has been done, which helps in developing a sustainable, cost-effective treatment processes. And it is categorized as a pollutants of poverty, in which sanitation-related organisms is focused towards the quality. And this class of pollutants is observed in rural areas. And further, the pollutants of growing prosperity, which comes under the second class, focused on the urban areas, which includes industrial waste and chemicals. And the last group, which focuses on the marine system, which includes both rural and urban areas, which is most alarming now with emerging pollutants as in micro levels as well as in nano levels in terms of plastics or personal and pharmaceutical products and PFAS and dyes and pesticides. So this now they have World Health Organization have categorized the pollutants based on these three different heads. So they are trying to group the different countries based on these different classifications, and they are trying to develop the process and implementing in a large scale. So out of these contaminants, we know that so many contaminants are there. Out of these contaminants, micropollutants emerges as a contaminants of concern, which is present at the micro to the nano level. The real challenge with these pollutants are towards the detection as well as the analysis. The cost-effective sensors or methods would help to track the transport of these pollutants either in the riverbeds or in any kind of a water reservoir, or it can be in a wastewater treatment plants also. So these micropollutants add to bioaccumulation as well as biomagnification phenomena, which is a very important concern with respect to living systems. And coming to this point, so many different categories of micropollutants are there, where pharmaceutical, personal care products, steroid hormones, surfactants, industrial chemicals, and pesticides. These are coming up with so many different subclasses are there, which we can able to sense in different kinds of water bodies in all over the world. And in this, we are going to target about this industrial chemicals, and we are going to deal some case studies with respect to the textile dyes, which are present in the riverbeds as well as in the industrial effluent treatment plants. So coming to the water treatment section, if you take, this is how the water is treated, and it is taken from the reservoir to the home. Like it starts from the raw water, many initial screening strategies will be there with respect to primary treatments, and followed by the secondary treatments and tertiary. Finally, it will reach the home. And if you take as an example as an industrial treatment, industrial wastewater treatment, there could be two. One is aerobic wastewater treatment as well as the anaerobic process, where the aeration will play a major role in treating the conventional detected waste materials which are present in the river and water streams. Later, it can be an anaerobic process also. Further and later stages of advancements, many anoxic reactors are also developed, which can able to target micropollutants to some possible extent. But when you come with the micro and nano pollutants, the treatment technologies which are available in the wastewater treatment plants are not sufficient enough to eliminate the pollutants as they pass through the different treatment processes. In a continuous process, it will be a really challenging one. So no specific treatment is now available to assure the complete removal of various micropollutants due to their diverse properties. And a lot of technologies are there at a primitive stage, wherein it needs a lot of improvements towards the scaling up ideas towards the real-time implementation. So when you take example with respect to the fate and transport of these micropollutants, that pose a very clear challenge in the wastewater treatment plants. The internal factors affecting the fate of micropollutants are its hydrophobicity nature, its biodegradable and volatile nature plays a very important role in determining the fate of micropollutants in water, as well as certain external factors also influences the fate of micropollutants. One is the nature of wastewater in terms of pH or temperature, and the competition which occurs between the other micropollutants, which means we can call that as a specific interaction between the different micropollutants also play a very important role when it comes to the real-time application in wastewater treatment plants. So there could be a lot of interactions as I specified here, a lot of electrostatic repulsion attractions are there, adsorption and absorption phenomena is there, which pose a very critical challenge at different phases of the treatment plants. And to cope up with this challenge, the conventional treatment methods may not be sufficient enough to deal with. So there is a need for advanced oxidation processes or advanced reduction processes, which will take care, which will take care of the micropollutants through its radicals, which are generated through its process. So many different kinds of advanced oxidation processes are there, like ozonation, catalysis, UV, that is photocatalysis or sonocatalysis, UV-based coupling with the H2O2, that is hydrogen peroxide, photo-driven Fentons processes, electro-driven Fentons processes. So many different advanced oxidation processes are there, which will generate a lot of radicals, which will take care of these degradation with respect to different pollutants. And all the micropollutants are different, processes are different, but the radicals generated from the processes we can able to shortlist to almost 10 to 12 different radicals. So we are going to play with the radicals towards the treatment of any kind of micropollutant. That is where now we are moving in. So in the earlier stages of development of wastewater treatment processes, the entire scenario were driven or oriented towards the process-based chemistry. But now most of the researchers have started to move towards a radical-based chemistry. We have started to look for a very specific kind of a radical generated through any kind of a processes, which will take care of the degradation systems. And the positioning of these AOPs can be after primary treatment, or it can be after a secondary treatment, or at the tertiary level. So based on the presence of the pollutant at the respective levels, we can incorporate these AOPs at an appropriate places. So with this, I would like to emphasize some importance about the different processes. First one is about the nano-coupled adsorption. Yes, adsorption, most of the researchers and most of the persons are working on adsorption. Now we have started to move towards nano-coupled adsorption. We can work with a lot of nano-composites or MOF or COF. A lot of advancements has been taken place in the nano-coupled systems, which will provide a larger surface area where the adsorption will be much more high, and the site-specific reactions is also possible when you're going with the nano-coupled adsorption. And when you come for the ozonation, it is a chemical oxidation process that employs ozone gas to oxidize the micropollutants. So through the, when you pass an ozone into a water, it will generate a lot of superoxide radicals as well as the hydroxide radicals. These radicals will take care of the degradation of the pollutants. So these oxidation can be of two important steps. One, it can be a direct oxidation, or it can be an indirect oxidation. Direct oxidation directly attacks the bond which is present in the micropollutant, and indirect oxidation generates the hydroxy radical, and these radical will take care of the degradation of the pollutants. So this is, though a lot of research has been taken place in the ozonation systems, the real challenge with respect to ozonation or ultrasonication lies in the scaling up systems. Cost-effective scaling up towards a larger scale application is a very big challenge. So those youngsters or those researchers who are focusing on these AOPs can take up these areas as their research of interest, so that fruitful ideas can be developed in this regard. And next to that is a Fentons process. Fentons process is an age-old process. It's the genesis of Fentons process is from almost 1930s. But a lot of advancements is coming up towards the modification of Fentons process by coupling with electric currents or through photo-driven processes like UV or visible lights. So these Fenton process generates, the conventional process is like either ferrous sulfate or ferric chloride reacts with hydrogen peroxide to generate this OH radical. This OH radical will oxidize the any kind of a pollutant into a mineralized form. right? So these reaction rate can be augmented by the addition by photons or by electric current. So hence it is referred as an electrophoton or photophoton. And right now the microbial fuel cells are also coupled with photon process to reap the benefits of the microbial system towards the degradation of the pollutants. And the next one is about the electrochemical oxidation. The electrochemical oxidation is also referred as anodic oxidation, which also generates different kinds of radicals. It not only it is like a homogeneous hydroxy radicals, it also generates different chlorine species by which we can able to take care of the degradation at a much faster rate. So many different modifications can be done in with respect to different electrode designs, like with titanium or iridium. So many different materials can be used to generate the different electrodes by which we can able to generate the different radicals, which will take care of the degradation of the pollutants. Next one is about the photocatalysis. This photocatalysis is always driven by the light. Either it can be a UV light or it can be a visible light. So this will play with the energy level between the valence band and the conduction band. So which will help in generation of the radicals, and these radicals will take care of the degradation. And finally, towards the hybrid treatment system. So each and every process will have its own positive points as well as the negative points. So now the treatment systems with respect to Western countries are moving towards a hybrid mode, where the positive aspects of the different methods are taken and they are augmenting towards each other. Thereby, the rate of degradation they are trying to improve to a much greater extent. So, and next to that, and so far we have seen almost about 6 different processes which we have seen. At the end of each process, we have seen that one radical is important. Radicals. So whether though we have started with the process, towards the end we are moving towards a different kinds of radicals which will help in degrading this pollutants. So when we try to categorize these pollutants, we can take you can see this table. In this table itself, we can able to see the fluorine is having a maximum potential of 3.06, and the hydroxyl radical followed by 2.8, oxygen ion is 2.42. These are all the different oxidation potentials of different radicals by which you can able to use it for the purpose of water treatment. And biohydrox, it is a modified version of this, which will include so many different metal organic frameworks and different biosystems to generate this potential. And right now, we are going to see the importance of this hydroxy radical. And towards the end of this session, we will be seeing some information about the sulfate radicals also. And towards the hydroxy radical, you can see from this slide, it is very clear that from a molecular oxygen towards a reduction as a result of an electron transfer, we can able to generate superoxide radical ion, peroxide ion, oxene ion, oxide ion. From oxene, with the addition of hydrogen, you can able to generate this hydroxy radical. What is the key difference between this hydroxy ion and radical, which is given in this slide, right top corner, I have given this. And what are all the key benefits of this hydroxy radical? One is it is highly reactive, and it is not, which is evident from the previous oxidation potential data also. And it is not selective. It is not specific. It will, whatever may be the type of the pollutant, it will degrade at a faster rate. And it can be easily generated. And it is very short-lived, and it is harmless also. But the real challenge is to control the rate of reaction. As the reaction rate is very fast, the controlling the rate of reaction will be a very big challenge when we are operating with hydroxy radicals towards the degradation of the pollutants, right? So these radicals can be generated. In this diagram I have given, these radicals can be generated through many different AOPs. And we have seen already what are the certain examples of AOPs: phentons, ionizing radiation, ozone oxidation, sonochemical system, photocatalysis, or oxygen or ozone, or supercritical water oxidation, and capacitive deionization. So many different methods are there to generate the hydroxy radical. But the real challenge lies in each and every process is that controlling the rate of reaction. How the reaction rate will be very fast. In order to monitor or in order to check the reaction kinetics, we need to be very strong with the analysis as well as with respect to the product chemistry. So next one, I will take one case study. This research is funded by Board of Nuclear Sciences, Bhabha Atomic Research Center. We have tried to develop a process for the degradation of industrial azo dyes by microbial as well as gamma irradiation. So India, though there are so many positive points are there with respect to India towards textile industry. India stands largest producer of so many different textile materials. It is the second largest producer. It contributes 18% to the industrial employment as well as 4% to the GDP. But if you take the negative side, you can able to see so many different challenges are there, out of which I am going to specify two. One is water demand for the processing as well as the effluent release impact on the environment. These two are concerned with respect to water. And you know that this image you might have seen in so many different presentations, that is 54% of India faces high to extreme water stress, which I have also specified in the introductory slide also. India ranks at the scale of 18% of quality with respect to supply of drinking water to the common people. And if you take, on the contrary, if you take with respect to the number of publications, the number of research publications is very huge. When you take almost the 60 years, you can able to see so many publications are coming up from the treatment of textile dyes with respect to different processes. It can be conventional process like adsorption, coagulation, or it can be towards an advanced oxidation process. So many publications are coming up, but still we don't have a much stronger system or developed scaled up process to be implemented in the industrial scale to a larger extent. So what all can be the challenges with that? The key important challenges with respect to industrial scale-up is most of the process developed in these publications are using the pH indicators and stains. If you take, it can be a methyl orange, it can be a methyl red, it can be a phenolphthalein, it can be a Congo red, it can be malachite green. So these indicators are least used in the textile industries. And most of the research coming up through using these these indicators, which may not be practically applicable in an industrial scale. And industrial effluent will be a mixed class of dyes. It will not be like a single class. It will be like a monoazo, diazo, polyazo, reactive, direct dyes, sulfonated dyes, non-sulfonated dyes. So many different classes of dyes are there. But when you come to the research purpose, most of the researchers, we will be focusing on only one specific class of dyes, which may not be practically possible when you are going for an industrial scale application. And the third important challenge is about the alkalinity nature and high saline concentration, high salt concentration in the industrial effluent. These two are the key important challenge which reduces the opportunity of bio-based system towards this application, because most of the microorganism cannot able to survive at a high alkaline condition as well as high saline condition. So that is where the component of AOP is coming up in towards the treatment of textile dyes. And most of the environmental engineers, we will be working towards handling large volumes of industrial effluent at short time. And the sludge management is also a key important challenge. So with this ideology, we have, with this work, we have tried to develop a process through microbial as well as gamma irradiation. And for this, we have taken 3 representative dyes, which are industrially used. One is reactive orange 16, which belongs to monoazo, reactive red 120, which is belongs to diazo, and direct red 80, which belongs to polyazo, as well as direct class. So we have taken care while selecting the dyes by which we can able to find a model in each and every classes of dyes. And it is a sulfonated dyes. And all the dyes we have taken are sulfonated. So these 3 dyes will belongs to azo class, reactive class, direct class, sulfonated class, right? And throughout the study, we are going to deal with only these 3 different dyes. And the microbial method we have developed through organism isolation, process parameters optimization, and the continuous packed bed reactor designs. So here you can see we have shortlisted 4 major sites for isolating the organisms, and we have isolated 36 different organisms, out of which we have selected 1 microorganism which is very strong in degrading these 3 class of dyes: reactive RO16, RR120, and DR80. And we named that organism as RAPT1. And later we have characterized that organism in a morphological and biochemical way. And we have molecular level characterization. And we have found that it belongs to Bacillus conii, and the strain name is RAPT. And we have deposited this in NCBI GenePank also. And later we started to, because since we have isolated this organism from a marine environment, we want to check what kind of a medium we can able to use it for the cultivation. So out of curiosity, we have tried with seawater taken from Rameshwaram and Tuticorin and Kanyakumari, which are sea coast in South India. And we have also tried with the 4% NaCl solution also. And interestingly, we found the first cycle of degradation took almost 11 hours in Rameshwaram, but during the after complete degradation, the second cycle took only 6 hours. The same kind of a phenomena you can able to observe in the second cycle of degradation across the different media. So the point is, this microorganism is highly capable enough to acclimatize to the different environments. And interestingly, within 4 hours of time, it could able to degrade 100 ppm of dye at a second cycle of degradation. So with this interest, we have moved towards the process parameter optimization, and we have taken contact time, number of cells, effect of NaCl, effect of pH, and effect of temperature, and concentration of dye. These parameters we have taken towards its relevance to the industrial treatment. And this effect of contact time will help in designing the reactor. The number of cells will try to minimize the load of cells so that the sludge load will also be minimized. The NaCl will provide an opportunity to see how far the microorganism can survive at a high saline environment. And at the pH also, the industrial pH is alkaline in nature. So we want to take the organism towards an alkaline nature. And the industrial effluent of the textile industries ranges from 30 to 50 degrees Celsius. And even it can go up to 60 degrees Celsius when it is using a reactive class of dyes in its unit. So the microorganism has to survive in higher temperature also. So based on these parameters, we have optimized the process, and the results are shown here. The effect of age of Bacillus organism. So you can able to see the 12th hour organism is taking a very less time to degrade. And with respect to effect of number of cells, the number of cells doesn't have any significant role. The 100 into 10 power 6 CFU units up to 500 into 10 power 6 CFU units there is no much significant difference. So we have taken 100 CFU units for our further study in order to minimize the sludge load towards the degradation. And towards the effect of temperature, yes, conventionally the 35 degrees Celsius shows a better results, but 45 degree also very less difference is there. Almost 10 units of difference is there between the 35 and 45. And with respect to effect of NaCl, the organisms glows very well at 4% NaCl, where the normal microorganisms cannot able to survive. So that is an interesting part of this research work, where we have isolated the organism from marine environment so that this organism have a native ability to survive at high saline conditions. And towards the pH, in acidic environment, obviously it is having a very less degradation efficiency. But when we are moving towards a neutral as well as the alkaline condition, the improvement in the degradation is there with respect to the system. So with this basic information, we started to design the reactor in batch and continuous mode. Before getting into the reactor design, the general mechanism of degradation of azo dyes involve two steps. One is from a reactive azo dye, it will form an aromatic amines when you subject it to anaerobic conditions. Then this aromatic amines will be converted into mineralized products like CO2 when you subject to aerobic condition. So these two stages are very, very important for a process of complete mineralization. So this mineralization can be achieved in two-stage reactors. Like first stage of reactor will be anaerobic, followed by the second stage, or you can create a microaerophilic conditions in a single reactor. So we are much interested towards a microaerophilic condition in single reactor. So with this idea, we have developed a small scale packed bed reactor system in a batch mode. And we have used polysulfonate foams for immobilizing this bacteria. And you can see in this slide, it is a very interesting one. The immobilization time took almost 12 hours. The 12 hours of immobilization shows a very promising results when compared to the higher immobilization rate. As well as the initial inoculum also, you can see 300 and 500 shows a much better analysis. And with respect to effect of substrate concentration, you can be able to see at 100 ppm, 92 ppm has been degraded. In 200, 94 has been degraded. In 300 ppm, 98 has been degraded, and 489. So you can able to see there is a kind of a saturation at a 300 ppm. After that, it is not going. So this particular system can able to degrade up to 300 ppm it can able to handle 300 ppm in a single shot. So we have interested to learn the kinetics of the system. So here you can able to see the rate constant is 0.0008 for immobilized batch and 0.0006 for the free cells. Here you can able to see the initial rate of reaction for the free cells is close to 1300, but in immobilized cells it is close to 1750. So which means this immobilization had shown up very promising results with respect to the batch mode of operation. So we have decided to improve to a continuous mode of operation. So in this study, we have fixed the certain reactor dimensions and reactor conditions for it. And this is the block diagram for the reactor design. And this is how the flow rate we have done. We have taken 4 different concentration at 100 milligram per liter, 200 ppm, 300 ppm, and 400. Each concentration is subjected to 44 hours of study, in which 0 to 20 hours we have maintained 75 ml per hour, and 21 to 30 for 150 ml per hour, and 31 to 40 at 225 ml per hour, and 41 to 44 as 300 ml per hour. So this is the reactor we have designed, and this is a kind of a textile dye we have collected from the industries, and it will be passed through this immobilized beads, which is immobilized with the microorganisms, and we have tried to optimize the process for all the 3 dyes. So this is the profile for all the 3 dyes. This is the percentage of degradation profiles for monoazo, diazo, and polyazo. And this is in terms of concentration for mono, di, and poly. So you can get a much better view in this particular table. Here you can able to see for 100 ppm, 200 ppm, 300 ppm, and 400. And this 3 is for the reactive orange, and this 3 is for reactor red 120, and this 3 is for reactor red 120. The elimination capacity is found to be maximum for the entire reactive orange 16 at this particular stage, which means at 300 ppm, at 300 ml per hour flow rate, the reactor is having the efficiency to clear 124 ppm of dye per hour. Similarly, for reactive red 120, it is having a capacity to degrade almost 119 ppm per hour is the elimination capacity rate. Similarly, for the reactive red 120, it is having a capacity to almost 20 ppm per hour. So which means the reactive dyes are having a very easy, this organism having a potential to degrade reactive dyes at a faster rate compared to the direct class of dyes. So this particular procedure may not be technically feasible for the real-time environment on a standalone process. So we are very much interested to augment this process by coupling with any other AOPs. So here you can able to see the residence time of this particular molecule for each molecule. So the residence time of this reactive red 80 is found to be close to 4 minutes, but other reactive orange and reactive red is very less. And you can able to see from this comparative data, the Bacillus conii free cells is having the capacity of 1300, and in the batch mode of packed bed reactor, it is having 1800, and during the continuous mode of operation, it is very close to 3000 ppm per day. So this is how the advancements has taken place in this particular regard, and this particular work is in trial in effluent treatment plant in Gujarat in support of Bhabha Atomic Research Center at a pilot scale level. And followed by, yes, from the previous slide, I have shown that microorganisms alone cannot be sufficient enough to take care of the complete degradation. So we are looking for some advanced oxidation process, and we are very interested to work with the gamma irradiation. And we have tried to optimize the process through several different techniques. And this is how the gamma radiolysis works. When you pass a gamma radiation through into a water, it will generate electrons, hydroxy radicals, hydrogen radical, hydrogen, H2O2, and hydronium ions. And in this, OH radical is having a very strong oxidation potential of 2.80, and this radical will take care of the mineralization. But still, we are not exploring the benefits of these radicals, these ions and radicals. So I will explain it in the next slides. So this is one kind of a work. We have tried to optimize the process of gamma radiation with reactive red 120 dye. So we have taken reactive red 120 dye as a model dye to develop the process of degradation. Here from this table, you can able to see this process of degradation works very well across the pH. So pH is not having any significant effect towards the process of evaluation. And from this table, you can able to see if I start a process with 3, during a degradation, the pH of value of the solution is getting decreased across all the pH, which means as a result of degradation, a lot of acids are getting generated, which lowers the pH towards the initial pH of study. Right. And further, we are very interested to work with the model reduction and transformation of the particular model which is generated from the process. So we have used this model kinetics towards the evaluation of the reaction kinetics. We can able to see by the addition of hydrogen peroxide, we could still able to improve the degradation to much greater extent with a dose constant of 0.6347, especially for the reactive red 80 dye. So this particular dye is very strong with respect to bio, but we can able to degrade this particular dye using the hydrogen peroxide in a with gamma radiation in a much easier way. So here, this slide explains about the significance. These two red marked radicals are reducing species, and this OH radical is the oxidizing species. Though in our earlier study, we are using this OH radical to the maximum benefit, but we are not using these electron as well as hydrogen radical towards the degradation. So we are very interested to use these radicals also by addition of the hydrogen peroxide. So here you can able to see with this equation, by addition of hydrogen peroxide, this electron interacts with it to generate the OH radical and OH ions, as well as this H2O2 also reacts with the hydrogen radical to form a OH radical. So this OH radical is a bonus for us, so that we can able to increase the rate of reaction, which is evident from this particular graph. So this is with respect to different dose of gamma ray, and this is with respect to different dose of hydrogen peroxide. You can able to see the increase in the dose constant till 0.87 across. You can see this middle line till this, it is improving, further it is decreasing. So which means beyond 1 millimolar, if you are increasing the hydrogen peroxide, the homologous recombination of radicals will take place. As a result of that, the availability of OH radical will become very less, which reduces the degradation rate, right? So further, we want to understand the sensitivity analysis with respect to the different dyes. Since we are working with the three important dyes of RO16, RO120 and DR80, we are very much interested to see how far the importance of these variables towards these radicals. So for that, we have tested with the artificial neural network with almost about 2,250 experiments. And we have trained the network for the three class of dyes. And as a result of that, we found that if effluent is rich in monoazo, then the dose of gamma ray plays a very critical role. And if the effluent is rich in RR120, equal importance has to be given for all the three parameters. And if it is on DR80, the more importance has to be given to concentration of H2O2 and dose of gamma ray. So this is a wonderful work by which we can able to understand how the dyes are influencing the selection of the input variables towards each and every processes. So later, we are interested to work with the process chemometrics. So using the mathematical equations, we are getting from the response surface methodology, or we can tell artificial neural network, can we able to use the benefit of partial differential equations towards much better predictions. So we have tried with the multivariate design and statistical analysis, where we have used the canonical correlation and rich correlations towards improvement of the predictions towards the applications of gamma irradiation towards the degradation of dyes as well as the antibiotics. Here you can see from this, this particular table, though it contains a lot of mathematical one, I will put it in a nutshell. This entire table number 1 concentrates about the canonical analysis of the predictions, and this concentrates about the ridge analysis. This particular thing is a consolidated table. So here you can able to see the CCF modeling predicted and equation based to predicted are very close to each other. And the experimental confirmation is very close to the mathematical computations of these models, so that we can able to minimize the applications of softwares, and directly we can go for the modeling towards the predictions in a much better way. So with the 2 slides, I would like to complete my session. In another 4 to 3 minutes, I will finish. So this is a kind of electrochemical systems we have developed in our lab. And through electric current, we have developed a process to degrade the dyes, industrial dyes. Here you can able to see the red colored one, and here you can able to see the complete colorless liquid. And all these processes we have developed using this electric current, and you can able to see this is red in color now. I will just fast forward it so that we can see the complete video within the time. So here you can able to see, as a result of the electric current with the modified system, we can able to achieve the complete degradation within a time of this. It is shown in the stopwatch also. Here you can able to see the final end, the degradation prevailing at the inlet site. Here you can able to see. So this is how the process we have developed using electrodes, which are very specific towards the anodic systems. Here you can able to see the complete colorless liquid. Though this contains traces of electrolytes, including chlorine, we have subjected this particular system into the membrane so that those salts can also be removed. And followed by this reactor studies is evident from the number of isobonds. We are very interested. I will put a complete slide in a nutshell. We are very interested to see how much radical is required when you are having a different number of bonds, because so many different dyes are there, so many different colors are there. We cannot able to go and target each and everything. So we are very interested to target how many bonds are there in the dyes. So that if 2 bonds are there, how many radicals we need to supply? If 4 bonds are there in a molecule, how many radicals we need to supply? So this particular is this is the target in our study. So based on that, we have developed reactors and with the different flow rates and different conditions. And we have given the slide informations in this particular thing. So the removal efficiency with respect to number of bonds we have established. And in this paper, we have worked on with 4 different bonds. With a molecule with the 4 different bonds we have tried to develop. And this is about, I just introduce it. It is a sulfate radical. This sulfate radical is upcoming now, having a much versatility than the hydroxy radical. Is highly versatile. It is having a very keen interest towards the researchers in degrading a lot of emerging contaminants, including the PFAS also. So this is a kind of a nano-coupled systems with thermal activated sulfate radical we have developed. Here you can able to see the change in colors within 10 minutes of degradation. So we have developed nano composites based on a ferrous as well as the biochar, and that catalyst, heterogeneous catalyst, we have used along with the persulfate system. So here you can able to see the complete degradation could be achieved within 15 minutes of time. The complete degradation is achieved. And with this, yes, and this is another work. I think I'm running short of time, so I'm not going to take much in detail about this. Sorry for that. And with this, I would like to acknowledge the funding agencies and the collaborators of our research group, Bhabha Atomic Research Center, TNSCST, and IAS, and Indian Institution of Engineers, and Academy of Sciences, and journal partners, as well as different collaborators working on the core areas of water with respect to different treatment methods. Either it can be a toxicological approach, it can be a process development, or it can be a reactor development. So I would like to acknowledge all my funding agencies, collaborators, and my research students, as well as the PhD scholars towards this work towards the water. So thank you, the entire team of IEI Tripura for giving me this opportunity, and especially Dr. Soma ma'am from NIT Agartala for giving me this opportunity. So looking forward your question and answer session later. Thank you.
Well, thank you so much, Dr. Padmanabhan, for your very expert deliberation and highlighting various water treatment processes, as well as your expert work in the field of removal of the dye based on recalcitrant from aqueous matrices using radical-driven advanced oxidation reduction processes. And also you have shown various modeling approaches for your particular research. This actually shows the quality of research which is being done in your particular lab, and thanks for showing this up to our participants. So thank you. So I'm sure there will be a lot of questions from our participants. I'd request you all to keep your questions ready with you, or you can also text us your questions in the question and answer section in the chat section. We'll be taking the questions at the end of the presentation of all the 3 panelists. We'll be taking all the questions all together. So please keep your questions ready. So moving on, next we have with us another expert panelist, Dr. Dipaloy Dotto from MNIT Jaipur. So welcome, sir. So it's my honor to introduce him in front of the August gathering. Dr. Datta is working as an assistant professor in the Department of Chemical Engineering at Malavia National Institute of Technology, MNIT Jaipur, Rajasthan. His research area includes reactive extraction, adsorption, separation, wastewater treatment, and process intensification. He obtained his PhD from BIT Pilani, Rajasthan. He has already completed 2 research projects received from the Waste Management Technology of DST and the Science and Engineering Research Board, DST New Delhi. Diploy ji has also contributed to around 70 research papers in peer-reviewed journals. He holds the professional membership of BITS SAA, IICHE, Indian Desalination Association, and Sports Engineering Association. And he also holds the position of Honorary Secretary of the Indian Desalination Association, BARC, Mumbai. So I now request Dr. Dipalo Datto to kindly start with this deliberation. All over to you, Dr. Datto.
Thank you very much. A very good evening. I hope the slide is very much visible.
Yes, sir. It's pretty visible. You can continue. Thank you.
Yeah, thanks a lot. So today in this session, I will be discussing on a simple topic, that is the application of the solvent impregnated resins for the treatment of wastewater. So this is a particular technique which is used along with the resin and the solvent. Okay, so this is the outline of my presentation: introduction, methods of preparation, how can you prepare this particular type of the resin, then their applications, then how you can regenerate it, and obviously the conclusion and future perspective. So this word that has been introduced in the year 1955, the word that is the impregnation. So in this first, the chromatographic method, this impregnated resin or a paper that was mainly impregnated with an ion exchange resin, and that was used for the chromatographic operation in 1955. So from there, the word emerged as impregnation. So then a laboratory method which was developed, impregnated ion exchange resin, which is in the ammonium form in filter paper. So there the filter paper was Dow X50 paper, and what they have prepared the uniform suspension of the resin and passed it over a strip of paper uniformly to get the desired impregnated paper with resin. Then this is used for the separation of different rare earth metals, and also that is used in the partial chromatography of heavy metals, trivalent and tetravalent ions. Next, Lederer and Rallo in 1962 used 3 ion exchange resin papers that were impregnated with 45% of sulfonic acid and 45% of quaternary ammonium and carboxylic acids. So that's how they have got 3 different type of impregnated resins. So this is again, they have used this again for the chromatographic separation of uranium, thorium from their solution of HCl and HNO3. But here the study, they mainly focused on the adsorption behavior of the organic network of the resin. So how the resin and the particular organic that is been introduced in the resin paper, how they form a particular organic framework. So that has been studied in this particular paper. And also how those solutes, they are that are removed by those ion exchange ion exchange resins, how they are interacting with the resin network, that is also been studied, and how the functional groups that are present both in the solid particles as well as in the resin part, how they been interacted, that is also been studied in this particular paper. So further studies that is been performed for the adsorption of inorganic substances from the solution containing organic solvent and the acid. So that's how the development of the solvent impregnated resin that took place at different stages. So here the separation of inorganic substances that is mainly found because of the formation of the complex. So they have found that this sulfonic and phosphoric group present in the amberlite Ac2 and zirconium phosphate paper, they mainly contributed to the they're basically making some complex with the resin, and that's how this impregnation this took place. Then another group, they have performed impregnation for the chromatography again on an amberlite IRA 400 and an anion exchange resin. So that was again impregnated in another resin, amberlite Ac2. So mostly it was initially it was basically the solid particles which were impregnated on the surface of another solid particle. Okay. So you can say this was a kind of immobilization of the particle on another solid particle. So here the separation that took place from the multi-component mixture of these components. Then this ion exchange resin in hydrogen form was impregnated on a paper, and they were used to separate weak organic bases, okay, dissolved in an organic solvent. So different type of separation that was been studied using this solvent impregnated resin. The separation dependent on the acidity or the basicity of the ion exchange resin paper and the solid. So that is very much important a parameter, the acidity and basicity of the ion exchange resin paper, and what kind of solute you want to separate from a particular aqueous stream. So that means choosing a particular type of ion exchange resin and a particular type of solvent, you can selectively separate out a particular solid from any kind of mixture. So again, they have in 1978 they have examined the metal retaining ability of polyurethane foam impregnated with LiX65 and Calx100. This is another kind of resin they have used, and here they have separated synthetic acid leach liquor containing this in a continuous column. So they have treated this solution. So there are many studies they are performed to find the application of solvent impregnated resin. Then in this study they have used a gel type and a macroporous and macroreticular polymeric resin for the impregnation of the solvent, and they have compared these two type of gel type and the macroporous type of polymeric resin for their separation. So what they have seen, because the impregnation that is very much important in a solvent impregnated resin, so this macroporous gel type of polymeric resin did not perform well. The drawbacks were that they did not solve in the presence of a diluent, so that the making of the impregnation process a difficult process here, because if they don't solve, then the solvent which is there, they may not penetrate easily inside the pores of the resin. But when they have used this macroporous resin, because of the cross-linked network that is available in this type of macroporous resin, and also the large number of pores and voids with diameter up to several armstrong that is available, so this macroporous resin became famous, or you can say attractive for the impregnation process as compared to the gel type. So why they are basically preferred? Sufficient number of pores that are present, large amount of solvent can be incorporated into this. These pores have good capability to retain the solvent, and obviously because of the good interaction between the solvent and the macroporous polymeric resin, the solvent will not leach from the pores of the resin. Also, they will provide with better surface area, high mechanical strength, and good chemical resistance. So that's why this macroporous type of resin that is been preferred over gel type, as they give or provide with twofold adsorption capacity. So this particular technique, or the solvent impregnated resin, this is a combination of three processes like adsorption. Because of the solid structure that is present, the adsorption of the solute will take place. Then because of the presence of the solvent, there will be interaction of the pollutant by solvent extraction. And also, if the resin is having some ionic configuration on its surface, then the ion exchange will also take place. And the solvent which is introduced, that may be a single solvent, or that may be a combination of the solvent that are basically incorporated into pores of the resin, and the resin acts as a support and gives the physical strength for the process. The solvent or the active compound to be impregnated should satisfy the following. So the solvent, basically they should have low viscosity. Now why they should have a low viscosity? Because they should easily penetrate inside the pores of the resin, and then it should have a very high binding capacity. It should interact with the surface of the resin, and it should get attached to the surface of the resin. Then it should have a minimal solubility in the aqueous phase, which is obvious. So the solubility should be minimum. The viscous or the solid solvent must be dissolved in some diluent before impregnation. So we need some diluent if its viscosity is comparatively high, or because we want to use them in very low amount. So this is the process in a in a diagram. So you can see the resin, the pores are there, then pore containing the solute. Then you have the solute in the aqueous phase. Then you will have the resin, and you will have the pores, which is the resin pore with the solvent. Then you have solute in the aqueous phase. Obviously, this solute will interact with the solvent which is present inside the resin, and that's how they will interact by making some complex like solute solvent complex, and they will get separated from the aqueous phase. So this is what. Now there are two methods by which you can impregnate the solvent. One is the wet method, another is dry method. So this is, first you have to prepare the resin or the support. So in that case, this support is that is being prepared by the bulk preparation method, and the impregnation that is been performed with an active material which we call the solvent, and the deposition is done from the aqueous solution through the liquid solid interface, the gas phase, the gas solid interface. Now sorry. Now, first is the dry impregnation. Now, in the dry impregnation, what is done? So, let's say we know the amount of the pore volume that is available with the resin. So, this much, same amount of the solvent that will be contacted with the resin, and that will be introduced, solvent that will go inside the pores of the resin. So previously dried support is conducted with volume of the solution equal to its pore volume. The solution contains the required amount of the active component. So it will only have the solvent and there will not be any diluent which is present. So as soon as the support is placed in contact with the solution is drawn into the pores of the resin by capillary suction. Okay, so generally in this case, in case of dry impregnation, there is no excess amount of solution that remains outside the pore space. Now what happens here, because some pores, the pores will have some kind of air, so it may happen that the pores are trapped or the air which is present in the pores, they are imprisoned and compressed under the effect of capillary forces. Okay, so that is one disadvantage or limitation of this process. What happens here in this case, at the time of the operation, there is a possibility the particular resin may crack or it may not attain the mechanical strength. So obviously this pressure that has been developed inside the impregnated gas bubbles, where gamma is the liquid gas interfacial tension and R is the radius of the bubble that is there. So force will be exerted on the portion of the pore walls in contact with these bubbles. So obviously walls are not strong enough and that may break, and that is the degradation of the mechanical property. So generally the dry impregnation that is not been followed. So that's why the wet impregnation. So here what can be done, a particular support that may be introduced in a diluent that is having the active component or the solvent into it. So the impregnation takes place in diffusional condition. The first phase of the saturation of the support by solvent involves the characteristics of the dry impregnation. In the second phase, when the diluent saturated support is added to the impregnating solution, high pressure is not developed within the pores. So this is one of the advantages, and there is a proper distribution of the solvent inside the pores by wet impregnation method. So the diffusion of the solvent within the pores, that is takes place by simple Fick's law of diffusion, and adsorption of the solvent onto the support mainly depends on the adsorption capacity of the surface and the adsorption equilibrium constant. So this is how the dry impregnation on the top figure and the bottom figure, which tells you the wet impregnation that is takes place. But in case of the dry impregnation on the top, you can see there is a air which may get trapped inside the pores of the resin. So this is mainly in dry impregnation. In addition to diffusion and adsorption, the pressure-driven capillary flow of the solution inside the empty pores that happens represented by Darcy's law. An important parameter is the solution viscosity, and the solution viscosity increases almost proportional with the concentration. So that means when you increase the concentration of the solvent, obviously the viscosity will increase, and that may hinder the diffusion of a particular solvent inside the pores in case of a dry impregnation. Then there are other methods which are also used for the impregnation other than the dry impregnation and the wet impregnation, that is phase inversion. Phase inversion or phase separation is a chemical phenomena exploited in the fabrication of the artificial membranes. So it is performed by removing the solvent from a liquid polymer solution, leaving a porous or solid membrane. So this is another method. Then using polymerization, so it is like wet impregnation method. The solvent dissolved in diluent is added dropwise, more useful for the preparation of impregnated membranes. So by polymerization also we can introduce the solvent. Then ultrasonication, again, which enhances the mass transfer into the pores, reduces the impregnation time, and this high ultrasonication power and high intensity of the ultrasonication field helps to penetrate more amount of solvent into the deeper pores of the resin. So that is another very much advantage of using ultrasonication in the wet impregnation method. And also ultrasonication, because of the ultrasonication, the equilibrium time or the saturation time for the impregnation, that also can be reduced because of the faster mass transfer which takes place inside the pores of the resin. So now you can increase the stability of the prepared SIR. So there are conventional conditioning, wet drying, or encapsulation that can be done to increase its stability. Then obviously the leaching of the solvent at the time of the use. So you should select the solvent and the resin in such a way there is a better bonding between the solvent and the resin pores, so that at the time of the utilization of the SIR or the solvent impregnated resin, the leaching of the solvent can be minimized. So there are these methods: conventional conditioning, excess solvent is removed, which is not attached to the surface. Adsorption, desorption of the solid molecules is preferred with SIR. Weakly attached solvent molecules detach from the surface of the SIR, leaving the stronger ones for a longer time. Then wet drying, boiling of prepared SIR done for several hours to remove any excess solvent. Encapsulation, coating of the suitable barrier which stops the leaching of the solvent and also which increases the stability of the SIR. And this encapsulation also ensures the stability of the solvent impregnated resin after several regeneration of the resin. So these are some then you have this drying. So drying is very much important so that the extra solute which is present may go from the surface of the. But I'm not going to this detail. Okay, so there is constant rate period of drying and the falling rate period of drying, which takes place in this solvent impregnated resin after the impregnation drying that is been performed. So basically, these are the steps which are followed for the preparation of the SIR. First is the washing of the original resin with kind of some reagent. So if some blockage in the pores that are present, that can go, and if some impurities, some resins, they are maybe having some impurity, so that can be removed in this washing stage. Then these are separated from the reagent by filtration. For that, you can use some paper or screen. Then further washing with DI water, deionized water. Then the filtration, again further drying, then impregnation, again filtration, and then drying. Okay. So these are the 8 steps which are being followed for the preparation of this impregnated resin. Another very much important point or characteristics of the solvent impregnated resin, that is the point of zero charge, or the at which the net charge on the surface of the resin becomes neutral, that pH that we have to determine, because once the pH is beyond the point of zero charge, which generally develop a net negative electrostatic charge on the surface of the resin. So that means the positive ions that can be easily separated by using this solvent impregnated resin. Again, if you decrease the solution pH beyond this point of zero charge, that may develop a net positive electrostatic charge on the surface of the resin, so which will facilitate more, or which will, the SIR will attract more negatively charged ions. So that means this point of zero charge should be determined for any kind of solvent impregnated resin, and this particular resin, by changing the pH of the solution, can be used for different type of solute molecules which may be anionic or cationic in nature. Now these are the types of the resin. So mostly they are macroporous resins, polystyrene cross-linked divinyl benzene type like amberlite XAD2, XAD4, XAD16, so and so forth. Then polar polymethyl methacrylate or acrylic base resin, then polypropylene base resins. These are available. Okay, so these resins are mainly, so based upon what type of solute you want to separate from a particular aqueous solution, we can use this. Okay. So these are different examples. There are pore structures, particle size, surface density, and the desired properties. It should have it should be porous, then chemically physically stable. Yeah, then the impregnated resin should not leach from the pores of the resin. The resin should have the capacity to retain the solvent, and obviously the equilibrium time, that is mainly depends on the structure of the resin, which is very much important, because that decides the time of the impregnation. Yeah. So I'll give you some more reading, because I think I was a little slow. So this is leaching that. Okay, so these are the different types of solvents which are used to impregnate, like amine based. There may be primary, secondary, tertiary, and quaternary amines. So this tertiary and quaternary amines that are mostly used in the treatment, in the preparation of the solvent impregnated resins. Then organophosphorus, like natural, you have phosphate base like TBP, phosphinates, phosphine oxides, then acidic phosphates, phosphoric acid, then phosphonic acid, then ionic liquids, phosphonium, ammonium type of ionic liquids. So these are the 3 main categories of the solvents which are impregnated. Then the characteristic, the choice of the solvent. So the solvents are responsible for the efficient performance of the SIR and the maximum recovery of the solid from the wastewater. So that's why the 4 types of amines that already we have seen. So mostly it is the quaternary amine that has been preferred over other amines. So more suitable for the removal of carboxylic acid, proton transfer or ion pair, making a complex with the acid molecule. Then bigger chain length of amine provides higher basicity with better removal efficiency as observed in the separation of carboxylic acids. So this is a typical kind of order which are found for the separation of the carboxylic acids. Then this is an example of quaternary amine, aliquot 336, which is also find many applications. Then organophosphorus, the category which already we have seen here. Then ionic liquids. Okay. There are other types also, like arena-based solvents that are available. Then the diluent. So this is they should have decrease in viscosity and facilitated solvent impregnation. So should have properties like they should non-viscous and low boiling. So easy transfer of the solvent molecules inside the pores. So that's why we need a diluent, which is, and also it should not react with the solvent or the resin. So these are numerous applications that are also used for the separation of the metals, acids. So you'll find numerous applications. Dilutants, resins, the solvents which are used. They are also used for the separation of the dyes also, then phenolic compounds. Okay. So the characterization, so many characterization techniques. So mostly these are the characterization techniques which are used for the characterization of the SIR. So this is one experiment which we have performed for the removal of the reactive dyes. So this is reactive orange 16. You can see the clear solution after the use of the solvent impregnated resin, and this is the resin after the treatment. Then we have used this in a packed bed reactor for the removal of reactive blue 13. This is a continuous setup where we have used 3 different columns for the removal of rhodamine B using aliquot 336 modified Amberlite XAD4 resin. Then here we have used the ultrasonication for the treatment of methyl orange dye. This is the treated sample. And then the recirculating flow vessel. This is also used for the treatment of dye solution. And the regeneration. So people have used many methods for the regeneration. Depending upon the type of the solute, the regeneration technique can be used. So the batch operation, the column map operation. So conclusion and future prospect. So there is a huge scope. This solvent impregnated resin can be used for different pollutants which are there in the aqueous solution, and obviously it is a combination of the process, adsorption, ion exchange, and extraction. So that's why it's the process is comparatively effective. So also it is seen that this is used for several regeneration is very much easy, and this resin can be used for several number of cycles. The only limitation that has been observed, it is if the impregnation is not done in a proper way, then there is a possibility of leaching of the solvent. Then the ultrasonication method could be an effective method to impregnate a particular solvent. For the drying, vacuum can be used, vacuum method can be used. There is a lot of scope. Now people are using the commercial resins. Natural resins can be used, and that's how the process can be made more cost effective. So for the further readings, you can refer to my articles on this solvent impregnated resin. Okay, thank you very much. Thanks a lot. I would like to thank the organizing committee and EI chapter of Agartala, Tripura, and especially Dr. Shoma Nag ma'am for contacting me and giving me this opportunity. Actually, sorry, today I'm suffering from swine flu, but still I'm here. So that's why my lecture was a little bit slow. Thanks a lot.
Thank you, sir. Thank you, sir, for your very detailed expert deliberation. We are glad that we could have you even when you are not good with your health. And you have very detailedly elaborated the application of this solvent impregnation for the wastewater treatment, and have actually highlighted the various insights about the resins. I'm sure our participants would be highly benefited from your particular deliberation, and whenever they want to venture into this particular area, they would be highly benefited from your particular deliberation. So thank you for giving us your time. Thank you so much, Dr. Dutta.
Yeah, thanks a lot.
So moving on, we have the third and the final panelist. He's none other than Engineer Pankaj Endurkar, a very dear friend of mine. He's working as a scientist in CSI Bhavnagar. So it's my privilege to welcome him. I'd like to share some details about Engineer Pankaj. He is currently working as a scientist in the Membrane Science and Separation Technology Division of the CSIR Central Salt and Marine Chemical Research Institute in Bhavnagar, Gujarat. He had completed his BTech in Chemical Engineering from Lakshminarayan Institute of Technology, Nagpur, and MTech in Chemical Engineering from NIT Rourkela. Previous to joining CSIR CSM CRI, he also worked as a junior works manager in the ordnance factory in Nalanda, selected through UPSC. His current areas of interest are optimization, adsorption, membrane separation, and especially for osmosis. He has published a lot of research articles in reputed national, international journals, and also have published numerous book chapters. So I'd request Pankaj to kindly limit his presentation within time, so that we could wind up our session within time. And there is an announcement for all the participants that if they do have any questions from their side, to kindly wait till Engineer Pankaj ji finishes his particular presentation, and then we'll be taking the questions one by one. And at the same time, if you have any doubts, you can also drop down your questions in the question and answer sessions. Our expert panelists can answer to your questions on a one-to-one basis also. So without any further delay, I'd like to request Pankaj ji to kindly start with his deliberation. So Pankaj ji, it's all over to you.
Thank you, Harjit, for introducing me. So here I am going to talk on forward osmosis process, membrane preparation and fundamental, and its application in the field. Okay, so before going into the deep into the topic, so we have to first understand what is the basics of water treatment. So we'll see introduction. Around 97.5% of water is a salt water. So among them, among 100%, 2.5% is a fresh water. So among 2.5% of fresh water, 70% is covered with icy and snow. Okay, so 30% is a groundwater and 0.3% is a fresh water, that is lake and river water. So this fresh water is uses for 70% in irrigation process purposes and 22% for industrial uses and 8% of this fresh water is used for domestic use. So you can say that the very less amount of water is available for the daily uses as a fresh water. So we have to treat this water with technologies, various technologies, which are membrane filtration, electrochemical separation, solvent extraction, coagulation, and external adsorption. So among these technologies, I'm going to focus on the membrane filtration technology because this is easily scalable at a large scale. Okay, and it is easy to operate also. So in the membrane filtration, there is 5 types like reverse osmosis, nanofiltration, electrochemical separation, forward osmosis, membrane distillation, and membrane bioreactor. So there are in the membrane filtration, what happens? There are 2 types of membrane used, that is the flat sheet membrane and hollow fiber membrane. In flat sheet membrane, what happens? The fabric is used for the support of polymeric membrane. In hollow fiber membrane, there is no fabric is utilized, so that this technology is useful for the preparation of water, treatment of waters. Okay, so next is there are 4 type of membrane available. So in the first type is microfiltration, whose pore size is around 100 nm, and ultrafiltration membrane whose pore size is around 10 nm nanometer range. So microfiltration remove the bacteria and suspended solid from the water, and ultrafiltration remove the viruses, bacteria, suspended solid. Ultrafiltration transport the water, monovalent ions, and multivalent ions. So next is the nanofiltration membrane. Nanofiltration membrane is it is the process where the viruses and bacteria and suspended solids is removed. There are some multivalent ions are transported through the nanofiltration membrane, and some multivalent ions are rejected from the nanofiltration membrane. So pore size is in the range of 10 to 1 nm. Okay. So next is the reverse osmosis. In this process, pore size is less than around 1 nm. So only water is transported through this membrane. Other ions like monovalent, multivalent viruses and bacteria are removed from this membrane. Okay. So basically, reverse osmosis is a pressure-driven process. So if the pressure is applied to the retention side, then water is transferred to the permeate side through the semi-permeable membrane. So this reverse osmosis is a less energy intensive process. It requires low temperature. So there is no additive required in the reverse osmosis process. So separation is mainly based on molecular weight of molecular weight cutoff. Okay. So this technology is easy to scale up. So there are some disadvantages also in the reverse osmosis process. Okay. So generally waste is produced generally 3 to 20 times as much as the product is produced. So that there is a huge waste is produced during the reverse osmosis process, and this is the costly process. Okay, for the installation and the maintenance cost of this process is very high. This process is high energy. In this process, high energy is required and high pressure is required. So that this is the cost of this reverse osmosis is increased. And this reverse osmosis process remove the healthy minerals present in the water. Okay, so it's calcium, magnesium, potassium, and other bicarbonate are removed from the reverse osmosis process. Okay, and when the RO is applied, so pH of the water is decreased. That's why the alkaline water treatment or any other RO are came into the existence in the market. Okay, so to mitigate this high energy require to mitigate the some disadvantages of the reverse osmosis process, like high energy requirement and high pressure requirement. There is another technology which is the forward osmosis process. This in this technology, what about the forward osmosis is the phenomenon of separation of solvent from the separation of water from the solvent with the help of semi-permeable membrane. But what happens? It uses this osmotic pressure. So in the reverse osmosis, what happens? It uses the hydraulic pressure. So here osmotic pressure is required to separate the water molecule from the solvent. So what is the osmosis? So osmosis is the movement of water molecule from the solution of high concentration of water molecules to the solution of lower concentration of water molecule. So what is the osmotic process? So osmotic process is defined as the minimum pressure that must be applied to the solution, which are the flow of solvent molecule through the semi-permeable membrane. So in this way, forward osmosis uses the osmotic pressure as a energy source for the separation. This is the formula of osmotic pressure calculation here. I is the one of C is the concentration, R is the temperature. Okay, so there are some key features on the forward osmosis process. It has very low cost because water is drawn due to the osmotic pressure gradient rather than the hydraulic pressure. So its energy consumption is very low because it requires very less energy because it doesn't require any pressure. Okay, and it has high water loss and lower the membrane quality. So there are in the figure you can see that there is a figure in this way you can see that the water molecule is transferred from the membrane.
I think there is some technical.
I think there is some technical issues. Okay, am I visible now? And my voice is audible?
Yeah, your voice is audible, sir, but I request you to share your slides.
Okay, yeah. Wait for 15 minutes.
Yes, sir, it's fine. You can go for full screen and continue, sir.
Okay, thank you.
Thank you. Please
Okay,
continue.
okay. There are a few applications in the application of forward osmosis which is in the emergency desalination, evaporative cooling, water pickup, and landfill leachate treatment, brine concentration, and food processing and osmotic power generation. Okay, so in osmotic power generation, it is used as it acts as a PRO. PRO means pressure retarded osmosis. Okay, so this is the schematic illustration of the forward osmosis process, where the feed solution contain the water, which is transferred from the membrane to the raw solution. So raw solution is then diluted. Okay, so if the raw solution is diluted, then raw solution recovery should be done to maintain the concentration of the raw solution. and the pure water has been produced with the help of this draw solution recovery techniques. Okay, the forward osmosis techniques mainly depend on the types of membrane and type of draw solution. Ideal draw solution should have a high osmotic pressure difference, which increases the flux of the membrane. Okay, so it should have high water solubility so that it increases the water recovery rates. Ideal draw solution should have lower molecular weights, which generate the high osmotic pressure. And the draw solution should have low cost generation and environmentally friendly. Okay, so the viscosity of the ideal draw solution should be less so that it increases the it minimizes the effect of internal concentration polarization. So there are some research scenario that has been done from the 2010. A4 process research has been increasing tremendously. Okay, so in the 2022 it is increased. You can see the graphs. Okay, among these research, 50% of the research has been done on the draw solution. Okay, so because the draw solution is very important in the forward osmosis process. So in the draw solution, maximum number of draw solution used were sodium chloride solution, and later on magnesium chloride, synthetic seawater, real wastewater, fertilizer, organic, potassium based draw solution, other sodium based draw solution, and synthetic draw solution, sodium bicarbonate draw solution has been extensively used for the research purposes. So coming to the membrane side of the forward osmosis, there are symmetric membrane and asymmetric membrane. Symmetric membrane means pores are a uniform diameter throughout the depth of the membrane. In asymmetric membrane, the pores are not uniform. Okay, so in asymmetric membrane, and it is an isotopic structure. Okay, there are two type of membrane used in the forward osmosis. That is thin TFC membrane, thin film composite membrane. It is another type of asymmetric membrane. Recently, what happened, the thin film nanocomposite membrane is extensively used in the forward osmosis process for the increasing the flux of the membrane. So what happened in the forward osmosis? What happened for the scaling of the forward osmosis is very less as compared to the reverse osmosis process. You can see the scaling is looser than the reverse osmosis process. Here the scaling is higher. So that these techniques can be used for the treatment of water. So effect of coming to the next effect of concentration polarization. So actually, what upon the concentration polarization will affect negatively to for the overall efficiency of any membrane-based separation process. There are two types of concentration polarization: internal concentration polarization and external concentration polarization. In internal concentration polarization, it occurs within the porous layer of the membrane. Okay, and external concentration polarization occur within the layer of the membrane. Internal concentration polarization is divided into two types: concentrative in ICP and dilutive ICP. This mode one is for PRO, means pressure retarded osmosis process, where the concentrative ICP occur at a feed site, and this mode 2 is a concentration is for the FO operation, where the dilutive ICP is occurred. Due to this internal concentration polarization, the flux of the membrane is reduced, and the osmotic pressure is ultimately reduced. So this dotted line indicate the concentration profile of the water, and this solid line indicate the concentration profile of the salt water. Okay, so this is draw solution concentration profile. So external concentration polarization is divided on concentrative ECP and dilutive ECP. So what is the recovery? How we can recover the raw solution? Here we can see the FO process can be marked means hybrid. Some hybrid system are utilized, which are forward osmosis and ultrafiltration membrane, forward osmosis and nanofiltration membrane. These are the some hybrid technologies like FORO and FOMD, FOED and FOTRO. So whatever diluted raw solution should be the concentration of diluted raw solution should be maintained here. So what upon the concentrated dilute solution is then passed to the NFRO or any MD recovery process. Then this reject from this NFRO or MD or any ultrafiltration or ED process, then reject is again send it back into the raw solution of the forward osmosis, so that in the permeate section you can collect a pure water. Now this is the hybrid ED and FO techniques, where in ED cation exchange membrane and anion exchange membrane is used, where the effluent from the ED is used for the feed of the forward osmosis, and draw solution NaCl is act as a draw solution. Here you can see that FO and PRO. FO means forward osmosis, PRO means pressure retarded osmosis. Here, what happened, the municipal wastewater retented is act as a feed for forward osmosis, and draw solution is act as a feed for the pressure retarded osmosis. So what upon the pressure retarded osmosis is used to generate the power. So seawater through the seawater brine, which is coming from the seawater desalination plant. Okay, and then after generation of power, the seawater is then sent back into the sea. Okay, in this way, the hybrid system can be utilized for the forward osmosis process. Here you can see the graph when the hybrid system is utilized. Energy saving is less in two-pass RO system, where if FO and RO is utilized, energy saving is higher. So in the hybrid system, the energy cut is there is a energy cut uses from 1.95 to 1.47 kilowatt hour per meter cube, and in FO-RO system, the dilute seawater by collecting from the secondary seawater is required roughly about 1.3 to 1.5 kilowatt hour per meter cube or minute. This in this way, this uses the less energy than the standalone single pass RO system, which typically 2.5 kilowatt per hour of energy uses. Okay, here 1.3 to 1.5 kilowatt hour meter square per meter cube energy is used. Here 2.5 kilowatt per hour meter cube of energy is used. That means it is the energy efficient process. This FO and RO hybrid. Therefore, FO can be utilized to treat the highly scaling saline before RO. There are some industry where the forward osmosis technology is utilized. So there are these are dairy industries where the treatment where the FO is used for the treatment of dewatering. Dissolved solute here is sodium chloride and sodium bicarbonate. Okay, so here what happened in dairy industry, forward osmosis and reverse osmosis hybrid technology is used, where the raw solution where sodium chloride. In this processing, forward osmosis process is used for the concentration of grape juice, tomato juice, pineapple juice, raspberry juice, and raw solution here is NaCl, calcium chloride, calcium nitrate, sucrose solution, high fructose corn syrup, and polyethylene glycol. And there is another food industry where the forward and beverages industry where the forward osmosis is used, which is used for the distillery concentration of distillery wastewater. The wastewater from the here the wastewater from the sugarcane molasses distillery will be act as a feed solution, and magnesium chloride will be act as a draw solution. It can also be used for the extraction of tea. Okay. And in chemical industry, forward osmosis technology can be used for the treatment of secondary effluent from the industrial wastewater treatment plant. And it uses industrial wastewater from the industrial ammonia absorption process as a raw solute in FO process. So that the forward osmosis is also used to dehydrate polyvinyl alcohol PVC latex before it is dried. Okay, so in the sugar industries, forward osmosis can be used to concentrate the sugar solution as well as the a liquid fraction of treated rice straw. So in the pharmaceutical industry, it is used to concentrate protein solutions like bovine serum, albumin, BS solution as a feed solution, and NaCl as a draw solution. In cold processing, it is used for treatment of wastewater from the mining. A hybrid FON NF system is utilized for the cocoa and wastewater treatment. In these technologies, cocoa and wastewater will be act as a feed solution, and NaCl, MgSO4, and calcium chloride will be act as a draw solution. Okay. Textile industry it is used to treatment the textile wastewater like dye wastewater can be treatment by using this technology. Okay, so here the draw solution can be utilized as NaCl, 2 molar per liter. In electronic industry, what upon the wastewater from the printed circuit board can be treated using this forward osmosis hybrid technology. So if there is a palladium containing wastewater in the feed solution, this feed solution is concentrated about 90% with the use of FO technology. And then if we do the electro extraction of the palladium metal, the palladium can be recovered using this method. So coming to the conclusion and future scope of this, we see whatever I have shown, that is only the lab scale result. So this technology must be must be scaling on a pilot or full scale. And this will be the next step, and more research need to be done on the performance of FO operation, like the draw solution performance, draw solution regeneration technology, high permeate flux combined with low concentration polarization, that should be studied, and membrane performance and fouling during the long-term operation, that should be studied for the FO performance, and membrane cleaning strategy also should be studied in the future, and reverse salt flux and substance diffusion through the membrane. This also be studied in the future. The membrane should be chemically stable and mechanically stable membrane required during the forward osmosis process. Where the draw solution required would have high water flux and low reverse salt solution. CSMCRI has started research on these forward osmosis technologies. Definitely in the future we will come with a very good result of this forward osmosis process. So thank you, and if anyone has any queries, so I will be happy to answer.
Okay, so thank you, Engineer Pankaj, for your very detailed deliberation on explaining about the various forward osmosis processes, as well as your detailed description about various other membrane-based water purification processes. I'm sure our young participants especially would have been highly benefited from your particular deliberation, and if they want to venture into this area of membrane-based wastewater treatment, they can definitely venture into that. And thank you for your very detailed deliberation. Thank you. So folks, here we end with the deliberation of all the three expert speakers. We have some questions from our participants who have dropped down some questions in the chat section. And along with that, if you have any questions that you would want to speak up to our expert panelists, you could raise your hands I'll give you the access to your microphone and you can come up with your questions. But before that, let me read down some of the questions. There's one question from Tamagna Ghosh. The question is, what is the treatment for sludge coming out of this particular process? I think what is the treatment for sludge coming out for this particular process? If I'm not wrong, maybe the participant is referring to the sludge description given by Dr. Padmanabhan, if I'm not wrong.
Yeah. Yes.
Yes,
Yeah.
sir.
Though I have answered it through chat, again I will try to answer it. Like most of the advanced oxidation process, we are trying to focus to minimize the sludge formation. So probably if you take ozonation, or if you take gamma irradiation or electron beam ray based radiation, the generation of the sludge will be much more limited, because these things will be in the micropollutant level. And the microorganisms which are used to degrade these pollutants will add to the sludge formation. But in case of electrochemical oxidation, if you take, a lot of sludge could be generated. And in Fenton's process also, a lot of sludge could be generated. And what we can do is a circular economy based approach will provide a much better opportunity to deal with. So if you take electrochemical oxidation or Fenton's reaction, probably the generated sludge will be highly rich in ferrous or the kind of a metals which is present in those electrodes. So those can be identified, and then possibly that can be channelized towards the respective industries, so that we can minimize that effect in the sludge formation. So that is one possible way by which we can able to treat the sludges to reduce the formation of sludge. Yes.
Okay, thank you. There's one more question from the same participant. The question is, can you focus some light on zero discharge technology?
So zero discharge technology is like to remove the all waste from a liquid system. So for example, if you are taking an example as a textile industrial effluent, you can expect a lot of textile dyes will be there. The fixing chemicals will be there. A lot of salts will be added to enrich the dye fixation onto the fabric. So all these things are considered as a pollutant with respect to textile industrial effluent. So the zero discharge technology is like, it will not restrict its application only towards the removal of dyes. It will also remove the salts. It will also remove the other kind of a dye fixing chemicals. And this particular effluent water will be treated enough for an irrigational purpose. So that is what the complete ideology about the zero discharge technology. It doesn't target only on one pollutant. It will try to create a perfect, or it will try to create a treated water in all aspects, which will be practically feasible for an irrigation systems.
Yes.
So that is how the zero discharge technology works. And to add this point, the membrane technology plays a very, very important role in generating this zero discharge technology system. Though we can develop a lot of AOPs or ARPs towards the removal of micropollutants, obviously these RO systems or NF or UF will play a very, very critical role in creating a zero discharge technology in a long run.
Yes, yeah, that's true. That's true. Along with this forward osmosis process, an upcoming technology which has got great potential to come up in this particular area. Okay, there's one open question. This question is open to all the panelists here. This question is from Mr. Bhaskar Sen, an Institution of Engineers corporate member. He's asking, does human immunity play a role? Does human immunity play a role? I mean, maybe he's referring to some kind of dyes. If somebody is consuming those dyes, whether human immunity will play any role in that. So
no, these if you take these pollutants, all these pollutants are immunogenic. That is what the last part of the work was specified about. So these dyes create a lot of respiratory issues to the workers, those who are working in textile industrial effluents or textile industries, or even in the treatment plants also.
right.
So these dyes, these PFAS or these pesticides or these micropollutants are classified under the head of recalcitrants, which means it cannot be degraded through a biological routes. So obviously there will be a lot of, though in human system, a lot of mechanisms are there to degrade these pollutants. Only it can handle only very limited concentration. So if you are working in a textile industries, you will be having a lot of chances to expose with the different classes of dyes, which cannot be degraded by the native enzymes like glutathione S transferase, which is an enzyme which is present in human system, which can degrade pollutants to very minimum extent. So that cannot be done. So obviously this will elicit a lot of immunogenic response also. Yes, human systems will elicit a lot of immunogenic response against that. One example what I can give to you is the arsenic contamination, which is present in most parts of the country here, will create a lot of cancer related issues and the skin related problems also, which you can able to witness through a lot of images. Through visual observations itself, it is very evident that these pollutants will create a lot of damages to the living systems, not only towards immunity, towards a lot of proteins related to replication or transcription or in generation of any kind of a metabolism. It creates a lot of damage. So that is where it is we are taking much concern towards a cost effective, as well as the degraded product should also not cause any harmful effects to the systems.
Right. Yes. Especially this arsenic contamination leads to some diseases, mostly cancer, and also skin related diseases are coming up. So one has to be very much aware of that. Okay, thank you, sir. So I think one last question. This question is from Nikhilesh. He's asking, what is brine concentration? Maybe this question is for engineer Pankaj. What is this brine concentration?
So brine concentration should be more than the seawater concentration. You know that the seawater concentration is around 35,000, more than around 35,000 ppm. So that so brine concentration is the reject of the seawater. Okay, so here the concentration is higher than the 35,000 ppm.
Okay, good. So there are some other questions related to sharing of these PPTs and recordings. So it is for the kind information of all the participants that the entire recording version of this particular webinar is available in the YouTube platform also. You can go and you can visit those videos, and there are lots of other videos are also there related to the various workshops and webinars that Institution of Engineers have already conducted. So you can go and refer to that. And regarding some more doubts, I'll request you to email to our this expert panelists. You already know their names, their affiliations. You can reach them up in their email, and you can get your doubts clarified. There is okay. There are some more questions, but maybe I can just take one or two more due to the paucity of time. Maybe one question I can take. Okay, the very last question: whether it is recommended to drink water purified by reverse osmosis, mineral salts are eliminated and is not good for our health. I think this will refer to Engineer Pankaj. So if you could just give some explanation to this particular question.
Actually, what happened is calcium, magnesium has been removed from the reverse osmosis process. So this is not good for the health. That's why the mineral cartridge is coming into the any other filter. So this there is another way, ultrafiltration process. So what happened, the reject from the ultrafiltration process, they doesn't remove the calcium magnesium. It is then connected with the product of the reverse osmosis. Then we can maintain the calcium magnesium in the product water. So in this way, we can maintain the product water, but calcium, magnesium should be required during the while drinking the water. Okay, this is most required.
Okay, sir. But one question from my side: what will you do if you have maybe some heavy metal contamination in your water? Will ultrafiltration help you up? Or do you need
actually, what happens in ultrafiltration, only bacteria will be removed. Okay, so for the removal of heavy metal contamination, reverse osmosis is used. But this process is very costly. Okay, because for the removal of heavy metals like like lead or any marker, it can be removed using this technology. But as far as I know, arsenic cannot be completely removed using this reverse osmosis. Okay, because it removes around I think 70 to 75% of arsenic. So it doesn't come into the WHO permissible limit. So this is not helpful for the removal of heavy metal. That's why there are some technologies which is known as adsorption. This is widely used for the removal of heavy metal like arsenic. For other heavy metals, RO can be sufficient.
Okay, okay. So I hope the question is now clear. So, okay, we are now nearing to the end of our this technical webinar. I would now request Dr. M.K. Debbarma, the Honorary Secretary of the Institution of Engineers, Tripura State Center, for delivering the vote of thanks. Dr. Debbarma, all over to you.
Thank you, Dr. Harjit. It's a nice presentation. We had a very good topic. Distinguished guest, ladies and gentlemen, I am audible.
Yes, sir, you are audible.
Okay, thank you. So a very good evening, one and all present here. It's my privilege to have to propose a vote of thanks in this IEI technical webinar on modern approach in the field of wastewater treatment, organized by IEI India Tripura Research Center under the aegis of Chemical Engineering Division Board, IEI Tripura Research Center. So first of all, I'd like to thank Dr. Harjit Nath, Assistant Professor and Head in charge, Department of Chemical and Polymer Engineering, Tripura University, who had accepted our invitation and introduced the panelist to the audience as a moderator of this today's webinar. I, on behalf of the Institution of Engineers, Tripura State Center, I'd like to convey our sincere gratitude to you. I also like to thank Dr. B.C. Padmanabhan, Assistant Professor, Department of Bioengineering, NIT Agartala, for sharing with us his findings and opinion today on this particular webinar, and we are grateful to him. We are also grateful to our Dr. Dipalay Datta, Assistant Professor, Department of Chemical Engineering, MNIT Jaipur, for demonstrating his views on modern approach in the field of wastewater treatment. Further, I must mention our deep sense of appreciation for our Dr. Pankaj Indorkar, scientist, Membrane Science and Separation Technology Division, CSIR, Gujarat, for inspiring and encouraging with us his words on this particular technical webinar. I also extend my thanks to Dr. Shubhadeep Bhattacharjee, PFIE Chairman, the Institute of Engineers, Tripura State Center, for his enormous cooperation in this organization to make it happen, this particular technical webinar. I'd like to thank all the distinguished participants, delegates, past chairman, past honorary secretaries, senior members, corporate members of IEI Tripura Research Center, who have given us particular time for their company today in this particular event. I also like to thank our various office bearers, those silent workers behind the scene. We can have this to make it happen to this webinar. So this is actually one approved program, which is called Continuous Professional Development Program of IEI, which is supported by our IEI headquarters. I also like to thank our technical director and all the officials from headquarters, those supported us this particular webinar. Once again, I want to state we're most grateful to all the speakers. This webinar, they have presented their technical findings also to the audience from various institutions for attending today's webinar in a large numbers. With that, I conclude my vote of thanks. Thank you very much, all of you again. Thank you. Thank you very much. Over to our moderator. I conclude this session.
So thank you, sir, for your vote of thanks. So with that, I thank all of you for joining, for giving a very precious time. Good night.